Step outside on a clear night, far from any city, and look up. The sky is dark. Not the soft dark of a dimly lit room, not the comfortable dark behind closed eyelids, but a deep and absolute dark, a darkness that seems to extend without limit in every direction, broken only by the faint, cold fire of distant stars. For most of human history, that darkness was simply accepted. The night sky was dark because it was night. The stars shone because they were there. The black between them was simply the absence of light, the void between the flames. But sometime in the 17th century, a question began to form in the minds of astronomers and natural philosophers that turned out to be far more troubling than it first appeared. If the universe is infinite, if stars extend in every direction without end, then every line of sight from every point in the universe should eventually terminate on the surface of a star. The entire sky should blaze with light, uniform and blinding, as bright as the surface of the sun in every direction. And yet the sky at night is dark. This is not a minor puzzle. It is one of the most profound observations in the history of science, a contradiction between the expected and the observed that took centuries to fully resolve, and whose resolution revealed something about the universe that is, in the most precise sense of the word, disturbing. The darkness of the night sky is not simply the absence of light. It is evidence of the universe's age, its expansion, its beginning. Evidence that the cosmos is not what intuition would suggest, not infinite, not eternal, not simply there. Tonight, we explore the darkness. We will ask what it is, why it exists, what it means, and what the full answer reveals about the nature of the universe we inhabit. The answer is stranger, and in some ways more unsettling than you might expect. And yet, held gently, it is also one of the most beautiful things that science has ever uncovered. We have the whole night ahead. There is no hurry. There never was. As we begin our journey tonight, let us start with the paradox itself, stated clearly, held carefully, appreciated for the genuine depth it contains. The puzzle is known today as Olbers Paradox, named after the German astronomer Heinrich Wilhelm Olbers, who described it in 1823. But the question had been raised earlier by Johannes Kepler in 1610, by Edmond Halley in 1720, and by the Swiss astronomer Jean-Philippe Loys de Chezeaux in 1744. Olbers receives the credit largely through the accident of historical memory, but the problem is older than his name. The paradox begins with a seemingly reasonable assumption. The universe is infinite, and stars are distributed throughout it, roughly uniformly. If both of these things are true, then consider what happens as you look outward in any direction. Near you, the density of stars is some value, call it a certain number of stars per cubic light year. Further out, the stars are more distant, and each individual star appears fainter. The inverse square law of light means that a star twice as far away appears 4 times dimmer. But as you look to greater distances, the number of stars in any given shell of space increases as the square of the distance. The shells become larger, containing more stars, precisely compensating for the dimming of individual stars. The mathematics works out exactly. In an infinite, uniform, eternal universe, the total brightness of the sky in any given direction should be effectively infinite, or at least as bright as the surface of the average star. Every direction you look should have a star. The sky should be as bright as the surface of the sun, everywhere, at all times. And yet the night sky is dark. This is Olbers' paradox. Not a paradox in the sense of a logical impossibility, but in the older sense, a result that contradicts expectation, that demands explanation, that refuses to be dismissed. It sat at the edge of astronomy for centuries, half noticed, half understood, waiting for the science to grow large enough to contain its answer. Let us follow the history of attempts to resolve Olbers' paradox, because the wrong answers are as illuminating as the right one, and they reveal how scientific thinking approaches deep problems. The most intuitive explanation, and the wrong one, is absorption. Perhaps the light from distant stars is simply absorbed by intervening gas and dust, before it reaches us. The darkness between the stars is not the absence of starlight, but starlight that has been swallowed by the material of the interstellar medium before completing its journey. This was proposed seriously and sounds reasonable, but it fails on examination. In a steady-state infinite universe, the absorbing material would itself heat up over time as it absorbed the light of infinitely many stars. Heated material radiates. Eventually, the absorbers would reach the same temperature as the stars they were absorbing and would glow as brightly as those stars. The darkness would be replaced by the glow of heated dust and gas, not eliminated. Absorption cannot solve the paradox. Another attempt invoked the finite number of stars. Perhaps the universe is not infinite but finite. Perhaps there are only a finite number of stars, and their combined light is insufficient to illuminate every point in the sky. But this merely relocates the problem. Why is the universe finite? What lies beyond its edge? Edgar Allan Poe, the poet and author, not a scientist, but a remarkably perceptive thinker, came remarkably close to the correct answer in an 1848 essay called Eureka. Poe proposed that the darkness of the night sky implied that the universe was young, that the light from the most distant stars had not yet had time to reach us. The sky was dark because the universe had a beginning, and its age was finite. This was an extraordinary insight for 1848. Poe was not working within any established scientific framework that supported it. He arrived at it by a kind of intuitive reasoning that anticipated, by nearly a century, the scientific consensus. The darkness of the sky is not a mystery about space. It is a message about time. As we continue our exploration of what the darkness of the sky reveals, we arrive at the discovery that transformed cosmology in the 20th century and provided a crucial piece of the resolution to Olbers Paradox. In the 1920s, astronomer Edwin Hubble, working at the Mount Wilson Observatory in California, was observing what were then called nebulae faint, cloudy objects scattered across the sky whose nature was still debated. Were they clouds of gas within our own Milky Way, or were they separate island universes, vast collections of stars at enormous distances? Using a class of variable stars called Cepheid variables, whose intrinsic brightness varies in a regular pattern related to their pulsation period, allowing their distances to be calculated, Hubble established that the Andromeda Nebula and other similar objects were far beyond the bounds of the Milky Way. They were, in fact, other galaxies, distant peers of our own, separated from us by millions of light years. This alone was transformative, but what Hubble found next changed everything. When the spectra of these distant galaxies were examined, their light was systematically redshifted, shifted toward longer wavelengths compared to the same spectral features measured in terrestrial laboratories, and the degree of redshift was proportional to the galaxy's distance. The further the galaxy, the more its light was shifted toward the red. Redshift of this kind indicates recession. The galaxies were moving away from us, and the more distant they were, the faster they were receding. The universe was not static. It was expanding. Every galaxy was moving away from every other galaxy, carried apart not by motion through space, but by the expansion of space itself. In this expanding universe, the light from distant galaxies was not merely dimmed by distance. It was stretched, its wavelength increased by the expansion of the space it had been traveling through. Photons that began their journey as visible light arrived as infrared, or microwave, or radio waves, their energy diluted, their light shifted beyond what our eyes can see. The expansion of the universe does not merely move the galaxies, it steals their light. It steals. It steals. Let us sit carefully with what the expansion of the universe actually does to the light that travels through it, because this mechanism is at the heart of why the sky is dark, and it deserves to be understood clearly. When a photon is emitted by a distant galaxy and begins its journey toward us, it travels through space. But space, in an expanding universe, is not static. The fabric of space-time is stretching every region of space, growing slightly larger with every passing moment. As the photon travels, the space it is traveling through expands. The wavelength of the photon, the physical distance between successive peaks of the electromagnetic wave, stretches with the space. A photon emitted as blue light with a short wavelength, might arrive after billions of years of travel as red light, with a much longer wavelength, or as infrared radiation, invisible to human eyes, or as microwaves. This stretching does two things. First, it shifts the light to longer wavelengths, where our eyes cannot detect it. Second, it reduces the energy of each photon. A photon of red light carries less energy than a photon of blue light, and a photon of infrared radiation carries less still. The energy that left the distant galaxy as visible light arrives, if it arrives at all, in a form that neither warms our skin detectably nor stimulates our retinas. This is part of why the sky is dark. The light from the most distant galaxies, red-shifted by billions of years of travel through an expanding universe, arrives in forms we cannot see with our eyes. But there is another, perhaps more fundamental reason, one that has to do not with the wavelength of the light, but with whether it can reach us at all. The universe has a finite age. Light travels at a finite speed. The combination of these two facts defines a horizon, a boundary beyond which no light has had time to reach us since the universe began. The sky is dark, in large part, because the universe is not old enough for it to be otherwise. As we continue, let us follow the light from the universe's earliest moments and discover that the sky is not, in fact, entirely dark, and that the light that fills it, invisible to our eyes, carries the most ancient message in existence. In the first 380,000 years after the Big Bang, the universe was so hot and dense that it existed as a plasma, a state of matter in which electrons and atomic nuclei have not yet combined into neutral atoms. In this plasma, light could not travel freely. Every photon was immediately scattered by the free electrons, trapped in a dense, opaque fog. The universe at that epoch glowed. It was full of light. But the light was imprisoned, unable to travel, unable to carry information, a brightness without reach. Then, as the universe expanded and cooled, the temperature dropped to approximately 3,000 degrees, the temperature at which electrons and protons could combine to form neutral hydrogen atoms. This event, called recombination, happened roughly 380,000 years after the Big Bang. At the moment of recombination, the fog cleared. The free electrons that had been scattering light were now bound into atoms, no longer available to scatter. The photons that had been trapped in the plasma were suddenly free to travel. The universe became transparent. Those photons, the light released at the moment of recombination, have been traveling ever since. For approximately 13.8 billion years, they have been crossing the expanding universe, being stretched by its expansion as they traveled. Their original wavelengths, in the infrared and visible portions of the spectrum, redshifted by a factor of about 1,000. Today, those ancient photons fill the sky. They arrive from every direction. They constitute what is called the cosmic microwave background, a faint, nearly uniform glow of microwave radiation that permeates all of space. The sky is not dark at microwave wavelengths. It blazes with the fossil light of the universe's first moment of transparency, the oldest light in existence, the afterglow of the Big Bang itself. Let us appreciate what the cosmic microwave background reveals, because it is one of the most information-rich objects in all of observational astronomy, and its existence directly answers part of our question about cosmic darkness. The CMB was first detected accidentally in 1964 by radio astronomers Arno Penzias and Robert Wilson, who were using a sensitive microwave antenna in New Jersey for satellite communication work. They noticed a persistent background noise in their instrument, a faint hiss coming from every direction in the sky, equally that they could not eliminate, regardless of how carefully they cleaned and calibrated their equipment. At one point, they famously attributed the noise to pigeon droppings in the antenna horn and spent time cleaning it out. The noise persisted. It was eventually identified as the cosmic microwave background, the prediction of which had been made by physicists George Gamow, Ralph Alpher, and Robert Herman in 1948, who had calculated that if the universe began in a hot, dense state, the cooled remnant of that primordial radiation should be detectable today. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. The CMB has since been mapped with extraordinary precision by satellites, including COBE, WMAP, and the Planck Observatory. These maps reveal that the CMB is almost perfectly uniform across the sky, and the temperature of the radiation varies by only about 1 part in 100,000 from one direction to another. This near-perfect uniformity tells us that the early universe was extraordinarily smooth and homogeneous. But the tiny variations, those 1 part in 100,000 fluctuations, are themselves extraordinarily informative. They are the seeds of all large-scale structure in the universe. The slight overdensities in the early universe that would, under gravity, grow into the galaxies, galaxy clusters, and cosmic web we observe today are written in these temperature fluctuations. The darkness of the visible sky is the other side of the CMB's existence. The light that once blazed at visible wavelengths has been stretched to microwaves, invisible to our eyes, leaving the visible sky dark while the microwave sky glows with ancient fire. As we journey deeper into our question tonight, let us ask something more precise than simply why the sky is dark. Let us ask how dark it actually is, quantitatively, measurably, with the exactitude that modern astronomy brings to the question. The background brightness of the sky, the total amount of light arriving from all sources, in all directions, minus the contributions of identifiable objects like stars and galaxies, is a quantity that astronomers have worked hard to measure. The challenge is significant. On the ground, the atmosphere itself glows faintly airglow, the chemiluminescence of molecules in the upper atmosphere, excited by solar radiation during the day and re-radiating at night, creates a background that swamps any extragalactic signal. To measure the true darkness of space, you must go to space. The New Horizons spacecraft launched in 2006 to fly by Pluto and continue into the outer solar system provided a remarkable opportunity for this measurement. As it traveled beyond Pluto, to distances more than 4 billion kilometers from the Sun, it moved into a region of the solar system where the contamination of background light measurements by solar system sources is minimized. The zodiacal light, the glow of sunlight scattered by interplanetary dust, is much reduced at those distances. Measurements made by New Horizons instruments in the outer solar system allowed astronomers to constrain the optical background light of the universe with greater precision than had been possible before. The results, published in papers in 2021 and 2022, suggested that the total background optical light, the integrated light of all galaxies across the observable universe, is approximately twice as bright as had been predicted from counting only the galaxies that Hubble had detected. This discrepancy, more light than identified sources can account for, has been interpreted as evidence that there may be additional sources of light that our current surveys have not detected, possibly very faint, diffuse galaxies, possibly intergalactic stars, stars that have been stripped from their parent galaxies and now drift in the spaces between, possibly something else. Even in measuring the darkness, the universe offers surprises. Let us explore one of the most profound and revealing observations in the history of astronomy, an observation that directly addresses the question of how populated the apparently dark sky actually is. In December 1995, the Hubble Space Telescope was pointed at a small patch of sky in the constellation Ursa Major, a region selected specifically because it appeared to contain nothing of interest. No bright stars, no known galaxies, no radio sources, just an apparently empty, dark piece of the sky. Hubble observed this patch for 10 consecutive days, accumulating light over approximately 150 orbits. The resulting image, the Hubble Deep Field, revealed something that silenced the astronomical community when it was first seen. The apparently empty patch of sky was not empty at all. It was full of galaxies. Approximately 3,000 galaxies appeared in an area of sky covering roughly 1/30,000,000th of the total sky. A patch, roughly the size of a tennis ball, held at arm's length, might subtend, but seen from much further away, some of the galaxies were nearby spirals and ellipticals, recognizable in their familiar forms. Others were smaller, redder, and more irregular galaxies, seen as they appeared billions of years ago in the universe's youth. The Hubble Deep Field did not merely show 3,000 galaxies. It demonstrated, through statistical extrapolation, that if this small, apparently empty region was representative of the sky as a whole, the total number of galaxies in the observable universe was far larger than previously estimated. The subsequent Hubble Ultra Deep Field, a longer, deeper observation, covering a still smaller patch of sky, revealed approximately 10,000 galaxies, and yet the sky appears dark. The darkness of the night sky is not the absence of sources. It is the consequence of physics, of expansion, of finite age, of redshift. The sources are there, beyond counting. Their light simply cannot reach our eyes in its original form. As we continue our exploration tonight, let us examine with precision the mechanisms by which the universe's darkness is created, because understanding the darkness requires understanding several physical effects working simultaneously. The first and most intuitive mechanism is simple geometric dilution. Light from a point source spreads outward in all directions. The total amount of light is conserved, but it spreads across a sphere whose surface area increases as the square of the distance. At twice the distance, the same amount of light is spread over 4 times the area, and only 1/4 as much falls on any given detector. At 10 times the distance, 1/100th as much. At 100 times the distance, 1/10,000th. This is the inverse square law. It makes distant objects faint. The second mechanism is the cosmological redshift we discussed, the stretching of photon wavelengths by the expansion of space. This reduces the energy of each individual photon by the factor by which the universe has expanded since the photon was emitted. For the most distant galaxies, this factor is enormous. A photon that left a galaxy when the universe was 1/10 its current size has been stretched by a factor of 10, its energy reduced to 1/10 of its emitted value. The third mechanism is time dilation. In an expanding universe, photons from receding sources arrive less frequently than they were emitted. If a source is receding and the space between us is expanding, the gaps between successive photons increase during travel. Fewer photons per second arrive than were emitted. This further reduces the apparent brightness of distant sources. The fourth mechanism, perhaps the most fundamental, is the finite age of the universe. The universe is approximately 13.8 billion years old. Light travels at a finite speed. No photon can have reached us from a source more than approximately 46 billion light-years away, the co-moving distance to the cosmological horizon. Beyond that horizon, the universe may extend indefinitely, but its light has not had time to reach us. Those potential sources are invisible, not because they are dark, but because they are out of reach. These 4 mechanisms together are why the sky is dark. Not mystery, not absence. Physics. 2. Consider the concept of the observable universe, the region of space from which light has had time to reach us, because it is central to understanding cosmic darkness, and it carries implications that are themselves somewhat vertiginal. The observable universe is a sphere centered on Earth, not because Earth is in any special location, but because any observer anywhere in the universe would see an observable sphere centered on themselves, defined by the same light travel time argument. The radius of our observable universe, corrected for the expansion of space, is approximately 46 billion light-years. This sphere contains approximately 2 trillion galaxies, as estimated from deep field surveys and statistical analysis. 2 trillion galaxies, each containing on average hundreds of billions of stars. The total number of stars in the observable universe is estimated at approximately 10 to the power of 24/1, followed by 24 zeros. More stars than there are grains of sand on all of Earth's beaches, by an enormous margin. And yet the sky is dark. Beyond the 46 billion light-year horizon, space almost certainly continues. The universe is likely far larger than our observable portion, possibly infinite. If the universe is infinite and uniform, it contains infinitely many galaxies and infinitely many stars. But we cannot see them. Their light has not had time to reach us. They are, in every observable sense, as if they did not exist from our vantage point. This is one of the deepest aspects of cosmic darkness. The darkness of the sky is not merely a statement about what is out there. It is a statement about what we can know, a fundamental epistemic boundary built into the physics of light and time, beyond which observation cannot reach. The universe may be infinite, but the universe we can observe is finite. And the boundary between the knowable and the unknowable is written in the darkness of the sky. As we journey further tonight, let us explore a different dimension of cosmic darkness, not the darkness of the night sky, but the darkness of matter and energy that fills the universe invisibly and constitutes the majority of its content. Dark matter is a form of matter that does not interact with electromagnetic radiation. It neither emits, absorbs, nor reflects light of any wavelength. It is, in this literal sense, dark, utterly, completely, observationally dark. No telescope, optical, radio, infrared, X-ray, or gamma ray can directly detect it. And yet we know it is there. The evidence for dark matter is extensive and comes from multiple independent observational lines. The rotation curves of spiral galaxies, the way stars in the outer regions orbit their galactic centers far faster than the visible mass of the galaxy can explain, require additional mass that we cannot see. Galaxy clusters contain far more gravitational mass than the visible galaxies within them account for. The precise pattern of temperature fluctuations in the cosmic microwave background is beautifully explained by models that include dark matter and is incompatible with models that do not. Current best estimates place the abundance of dark matter at approximately 27% of the total energy matter content of the universe. Ordinary matter, the atoms that make up stars, planets, gas, clouds, and everything we can directly observe, constitutes only approximately 5%. The universe is not mostly stars and gas and galaxies. It is mostly darkness. Dark matter forms the scaffolding on which the visible universe is built. It gathered first, forming the gravitational wells into which ordinary gas fell and formed galaxies. The cosmic web, the large-scale structure of filaments and voids, is primarily a dark matter structure, with the luminous galaxies merely tracing its densest regions. What dark matter actually is, what particle or particles compose it, how it was produced in the early universe, remains unknown. It is one of the central unsolved problems in modern physics. Let us explore the second component of cosmic darkness, the one that is, in some respects, the most disturbing of all. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. We have discussed it in earlier explorations. But tonight, it deserves particular attention in the context of darkness, because dark energy constitutes approximately 68% of the total energy content of the universe. It is the dominant component. More of the universe is dark energy than dark matter and ordinary matter combined. And we have essentially no idea what it is. The term dark energy is, in this sense, less a description than a confession of ignorance. We know it has energy because its effect on the expansion of the universe is real and measured. We know it fills all of space. We know that its energy density appears to be constant, or very nearly so, even as the universe expands, which distinguishes it from ordinary matter and radiation, whose densities decrease as the universe grows. The most natural candidate for dark energy is the energy of the quantum vacuum, the zero-point energy that quantum field theory assigns to empty space. The problem is that when physicists calculate how much vacuum energy quantum field theory predicts, the answer is approximately 120 orders of magnitude larger than the observed dark energy density. This discrepancy, a factor of 10 to the power of 120, is sometimes described as the worst prediction in the history of physics. Something is reducing the vacuum energy to its observed tiny value, or some other mechanism is responsible for dark energy, or our theoretical framework is incomplete in some fundamental way. We do not know which. What dark energy means for the long-term fate of the universe is stark. Its accelerating effect on expansion will, over billions of years, push every galaxy beyond the local group, outside our observable horizon. The universe will become darker, not lighter, as time passes. The islands of light will grow further apart, and each will eventually be alone. The darkness is not merely the present condition of the universe. it is its future. As we continue our journey through the darkness of the cosmos tonight, let us visit the places where darkness is most complete, the cosmic voids, the vast regions between the filaments of the cosmic web where almost nothing exists. The cosmic web, the large-scale structure of the universe, organizes matter into filaments, sheets, and nodes, with galaxy clusters at the intersections and long threads of galaxies connecting them. Between these luminous structures lie the voids, enormous, roughly spherical regions of space, largely empty of galaxies. The word void in this context should not be underestimated. These are not merely regions of lower than average galaxy density. They are regions where galaxies are almost absent entirely, where the matter that would otherwise be present has been drawn, over billions of years, into the surrounding filaments and clusters by gravity. The typical cosmic void has a diameter of tens to hundreds of millions of light-years. The largest known void, if it is indeed a single connected structure, is the Boötes void, approximately 330 million light-years across. If our Milky Way were located at the center of the Boötes void, the nearest large galaxy would be invisible to the naked eye from Earth. The sky would appear almost starless beyond our own galaxy's stars, the surrounding universe hidden behind hundreds of millions of light-years of near emptiness. Inside a cosmic void, the darkness of space reaches its most complete expression. The nearest galaxies are far away. The cosmic background radiation is the same as everywhere, but the visible light from any direction is minimal. The sky, seen from within a void, would be profoundly, almost absolutely dark between its own local stars, the broader universe hidden not by any physical barrier, but by simple distance and the dilution of light across vast, empty space. Voids occupy the majority of the universe's volume. By some estimates, voids account for approximately 80% of the total volume of the observable universe. The luminous structures, the galaxies and their clusters fill only a small fraction of the space they seem to dominate. The universe is mostly void, mostly darkness. The light is the exception. Let us descend further into the darkness and consider the nature of intergalactic space, the vast regions between individual galaxies. Between the Milky Way and the Andromeda Galaxy, a distance of approximately 2.5 million light-years, lies a region of space that is not quite empty, but approaches emptiness more closely than anything achievable in a laboratory on Earth. The intergalactic medium, the tenuous gas filling the spaces between galaxies, has a density of approximately 1 particle per cubic meter in typical regions, and considerably less in the voids. A cubic meter of the best laboratory vacuum achievable on Earth contains more residual particles than a cubic meter of intergalactic space. The temperature of intergalactic gas varies enormously. In the warm-hot intergalactic medium, a diffuse, widespread phase thought to contain a significant fraction of all ordinary baryonic matter in the universe. Temperatures range from approximately 100,000 to 10 million degrees Celsius. Not cold, but so diffuse as to be observationally nearly invisible. High temperature, combined with extremely low density, means almost no emission of light. No dust, no clouds, no weather, no seasons, no particles moving through space with any regularity. And the light that exists there, the photons crossing intergalactic space, do so at the speed of light, taking millions of years to cross from one galaxy to another, in a darkness broken only by the faint background glow of the cosmic web's own thermal emission and the ancient microwave light of the CMB. This is what most of the universe is, not stars, not galaxies, not the rich complexity of solar systems and nebulae that fill our imagination when we think of space. But this, the intergalactic void, cold, diffuse, nearly empty, and profoundly dark. The stars and galaxies that make the universe beautiful are, in terms of volume, vanishingly rare. As we continue our exploration of cosmic darkness, let us return to Earth and consider something that is closer and more immediate, what most of humanity has lost in recent generations. For all of human history until approximately a century ago, the night sky was a universal experience. Every person on Earth, on any clear night, could look up and see essentially the same sky, the full Milky Way arching overhead, thousands of stars visible to the naked eye, the deep and absolute darkness between them that this entire exploration has been about. That sky is now invisible to approximately 80% of the world's population. Light pollution, the scattering of artificial light upward into the atmosphere, creating a diffuse glow that drowns out the natural darkness of the sky, has transformed the visual experience of the night for most human beings alive today. In cities, only the brightest stars are visible. The Milky Way is unknown to most urban residents, except through photographs. The deep darkness that our ancestors saw every cloudless night has been replaced by an orange or grey ambient glow that never fully darkens. The Milky Way is no longer visible from the locations of 60% of Europeans and nearly 80% of North Americans. In the most light-polluted regions, the great metropolitan areas of the developed world, the night sky contains perhaps a few dozen visible stars on what would otherwise be a night of thousands. This is a loss that is difficult to quantify but real. The human relationship with the night sky spans all of recorded history and deep into prehistory. Every culture that has left records has records of the stars, navigation, agriculture, mythology, religion, calendars, and cosmology, all built on the foundation of a dark sky clearly seen. That foundation has been eroded in a single century of electrification. The darkness we have been exploring tonight, the profound, physics-laden darkness of cosmic space, is now available to most people on Earth only through photographs and documentaries. The direct experience has been covered over by light. Consider the growing global movement to recognize and protect dark skies, and what that effort reveals about the relationship between darkness and the full experience of being human. The International Dark Sky Association, founded in 1988, has worked to raise awareness of light pollution and to certify dark sky preserves, parks, communities, and other areas that commit to limiting artificial light and preserving the natural darkness of the night. As of the mid-2020s, hundreds of dark sky places have been certified worldwide, from national parks in the American Southwest to the Brecon Beacons in Wales to reserves in New Zealand, Chile, and beyond. These are places where the night sky can still be seen, as it was seen by all human beings throughout most of history. The effort is not merely sentimental. Light pollution has measurable ecological consequences. Many species, insects, birds, marine animals navigate, reproduce, and regulate their biology by natural light cycles. Artificial light disrupts these cycles, with consequences for ecosystems that are still being studied. Sea turtle hatchlings that should navigate toward the brighter horizon of the ocean are drawn instead toward coastal lights. Migratory birds collide with illuminated buildings. The nocturnal insects that pollinate nighttime flowers are disoriented and killed by artificial light. But the human dimension is real too. There is something in the experience of a truly dark sky, in the direct visual encounter with the full Milky Way, in the sense of depth and scale that only a darkness uncontaminated by artificial light can provide, that connects people to the universe in a way that no image on a screen can fully replicate. The paradox of our age is that precisely as our scientific understanding of the universe has deepened most dramatically, precisely as we have discovered the CMB, resolved the Hubble Deep Field, mapped the cosmic web, measured dark energy, most human beings have lost direct access to the sky that those discoveries are about. We understand the darkness better than ever, and we experience it less. As we move into the philosophical territory that always seems to open at the edges of the best scientific questions, let us sit with what the darkness of the cosmos means, not merely physically, but in the larger sense. The darkness of space is, at one level, simply a physical fact. It is the consequence of the universe having a finite age, of light traveling at a finite speed, of expansion stretching photons beyond visible wavelengths, of most of the universe's content being dark matter and dark energy that emits no light at all. These are all measurable, quantifiable, explicable facts. But the darkness also carries something that resists reduction to measurement. There is a particular quality to the darkness of a truly clear, dark sky that has been recognized and valued by human beings across all cultures and all of recorded history. It is a darkness that does not feel empty. It feels full of depth, of scale, of time. Standing under a dark sky and looking up, the eye and mind are drawn into something that does not end. There is no ceiling. There is no wall. There is only depth, extending outward without discernible limit, speckled with the cold fire of stars so distant that their light has been traveling for years, decades, centuries. This experience, the experience of the dark sky, is one of the few contexts in ordinary human life in which the true scale of the universe becomes somewhat viscerally available. Not intellectually available the way a book or a screen can make it intellectually available, but viscerally, bodily available. The darkness presses in from all directions. The stars are not decoration on a ceiling. They are holes in a thin sheet of the familiar world, behind which the real universe extends. The darkness is not disturbing in the way a dark room is disturbing. It is disturbing in a different, older sense. It disturbs the ordinary assumption that the world has a scale comprehensible to a human being. Let us return, near the end of our exploration, to the word in our title, disturbing, and be honest about why the full answer to the question of cosmic darkness earns that description. The resolution of Olbers Paradox, the reason the sky is dark, is, as we have seen, the finite age of the universe. The universe began. It has not always been here. The light from sources beyond our cosmological horizon has not had time to reach us. This is, in a certain light, deeply strange. The darkness of the night sky is not a simple absence. It is evidence of a beginning. It tells us, through a simple observation available to any person on any clear night, that the universe is not infinite and eternal, that it has a history, that there was a moment, approximately 13.8 billion years ago, before which there was nothing, or at least nothing, that our current physics can describe. The darkness carries the signature of the Big Bang. Every dark patch of sky between the stars is dark because the universe is not old enough to have filled it with light. And the future of that darkness is, in its own way, also disturbing. As dark energy continues to accelerate the universe's expansion, the observable universe will grow darker over cosmic time. The galaxies beyond our local group will recede beyond the cosmic horizon. The stars within galaxies will exhaust their fuel. Over timescales of trillions of years, the universe will transition from its current stelliferous epoch, the age of stars, to a long, slow cooling. The last stars will burn out. The last black holes will evaporate through Hawking radiation. The universe will approach a state of maximum entropy, maximum darkness, from which no further evolution is possible. The darkness we observe tonight is not the final darkness, but it points toward it. The night sky, in its beautiful, profound, physics-laden darkness, is a window on both the beginning and the end of everything. As we approach the final moments of our journey, let us turn toward what is, perhaps, the most important question. Not what the darkness means, scientifically or philosophically, but what it means for the experience of being alive in this particular universe at this particular moment. The darkness of the cosmos can be experienced as isolating. The scale of the voids, the near emptiness of intergalactic space, the eventual fate of an increasingly dark universe, these can press on the mind in ways that feel, if dwelt upon, in a particular frame, lonely. But there is another way to hold it. The darkness of the cosmos is the context in which every light is visible. The stars are visible because the sky around them is dark. The galaxies in the Hubble Deep Field are visible because the background against which they glow is essentially empty. The cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang, is detectable because it shines against a background dark enough to reveal it. Without the darkness, there is no light. Without the void, there is no structure. Without the empty space between the stars themselves would be invisible, lost in a uniform blaze of light, indistinguishable from its background. The darkness is not the absence of the universe's significance. It is the medium in which the universe's significance is expressed. And perhaps there is something in that for the human experience of quiet and dark and stillness. The times of darkness, the quiet nights, The silences between words, the empty spaces in a life are not necessarily the times of absence. They are sometimes the times when the lights that exist become most visible, when what matters is most clearly seen against a background of stillness. The universe is mostly dark, and in its darkness, the light that exists is extraordinary. And so we arrive, gently and without hurry, at the end of our journey together tonight. We began with a simple question: how dark is space, really? And we followed it into territory that proved to be, as promised, more layered and more profound than the question first suggested. We explored Olbers Paradox, the centuries-old puzzle of why an infinite universe full of stars should have a dark night sky, and we found that the darkness is not a mystery to be swept aside, but a message to be read. A message about the finite age of the universe, about its beginning, about the speed of light and the expanding fabric of space-time that stretches the light of distant galaxies beyond the wavelengths our eyes can detect. We visited the cosmic microwave background, the afterglow of the Big Bang, filling the entire sky with ancient light invisible to our eyes, a faint microwave glow that is the most distant thing we can observe and the most ancient light in existence. We measured the darkness with spacecraft beyond Pluto and found that the sky is brighter at optical wavelengths than the galaxies we can count would explain, hinting at sources of light we have not yet found. We stood at the edge of the Hubble Deep Field and watched 3,000 galaxies emerge from a patch of sky that appeared empty. We explored dark matter, the invisible scaffolding that constitutes 27% of the universe's content, and dark energy, the still more mysterious component that makes up 68%, that fills all of space and drives its accelerating expansion, and about whose fundamental nature we are largely ignorant. We traveled into the cosmic voids, those vast, nearly empty regions that constitute the majority of the universe's volume, and we sat with the intergalactic medium, the near-perfect vacuum of the spaces between galaxies, cold and sparse and profoundly dark. We returned to Earth and considered what most of humanity has lost, the direct experience of a dark sky covered over by the light pollution of a century of electrification. And we recognized that even as our scientific understanding of the cosmos has deepened most dramatically, the simplest, oldest, most available portal to the experience of cosmic scale has been closing for most of the people alive today. And we sat, at the end, with what the darkness means, not merely physically, but as a feature of the universe that has shaped human consciousness, human culture, human inquiry. Since the first being capable of wondering looked up at the night sky and felt the depth of it pulling at something it did not yet have words for. Tonight, wherever you are in a city whose sky glows with reflected light, in a rural dark where the Milky Way is visible if you step outside, in a room with curtains drawn against the night, the same universe extends above you, the same darkness, the same physics. The photons of the cosmic microwave background are passing through you right now as they pass through everything, continuously, having traveled for 13.8 billion years, from the moment of the universe's first transparency. You are bathed, at this moment, in the oldest light in existence. You do not feel it. It does not warm you, but it is there. The light from 2 trillion galaxies, redshifted and diluted, and mostly beyond the wavelengths your eyes can see, is arriving from every direction. The photons that left distant galaxies millions or billions of years ago before Earth existed, before the Sun formed, in some cases, before the Milky Way had assembled its current form, are completing their ancient journeys and ending them, quietly and unannounced, in the fabric of the room you rest in. You are not separate from the darkness. You are inside it, surrounded by it, bathed in the ancient, invisible light that fills it. The darkness of space is not empty. It is full of photons too old and too stretched for our eyes, of dark matter flowing silently through everything, of dark energy stretching the fabric of space-time outward in every direction, of the deep and patient physics of a universe that began and will end in ways that transcend our ordinary categories of time and meaning. The night sky is dark, and in that darkness, if you know how to read it, is written the entire history and future of the universe. Rest now in the ancient light that surrounds you. The universe is mostly dark, and it is magnificent. Thank you for exploring with us tonight. May your rest be as deep as the spaces between the galaxies, and as full of quiet, invisible light as the night sky has always been, whether we can see it or not.